Okay, I think we can start. So welcome everyone to our ITMP seminar. And today we are happy to have Sandipan Kundu, and he will speak about closed strings, higher spins, and causality. So please start.
Hello, everyone. Thank you so much for the invitation. So this talk is based on these two recent papers of mine with Gerard Kaplan. Oh, before I begin, let me just say that, like, if you have any question at any time, please feel free to interrupt me. Otherwise, I'm just screaming at my computer. Okay, so the main idea is very simple. So the goal is to impose constraint on the space of consistent QFTs just from general principles and symmetries. In recent years, the success of, for example, the conformal bootstrap program taught us that this is indeed a very powerful idea. You can get a lot of mileage out of just these general principles and symmetries. However, this is not a new idea. So there are many examples of the same basic idea, and even in 60s, 70s, and 80s. One of my favorite example of this idea is the bound on massless high-spin particle in nature. So if I give you quantum mechanics and special relativity, and I ask you to write down consistent theories of massless high-spin particles, what you get is the following. You can show that the menu of the massless particle is a short one. So massless particles can only have spin 0, half, 1, 3/2, or 2. That's it. All the higher spin massless particles, they are ruled out. They cannot be made consistent with both quantum mechanics and special relativity.
Are you in Minkowski space or?
Yes, it's in Minkowski, yes. Even in ADS, there is a similar statement, but I'll not talk about it. Okay, let me not talk about ADS. There is a similar statement, but there you can actually have an infinite tower of massless particle with unbounded spin.
Yeah. Also, another question related. When you refer to Witten-Weinberg work, I mean, what exactly you mean? Because roughly speaking, in this paper, they have a footnote showing that following these arguments, you rule out spin 1 massless particle as well.
Yeah, mainly I'm focusing on the second reference by Poratti here. It's basically there in that paper, Poratti showed basically, like, if you consider gravitational interaction, anything with spin greater than 2 cannot have any massless particle with spin greater than 2 cannot have a graviton 3-point function which is consistent with the soft theorem. Okay, let me also mention that actually, as you increase the spin, it gets more constraining. So if you increase the spin, the system gets more and more constraining. What I mean by this is the following. You can have as many massless spin 0 particles as you like in your theory, that's okay, but you can only have one spin 2 massless particle, which is also known as the graviton. Not just that, even the long distance interaction of any particle x with the spin 2 massless particle graviton, the long distance interaction of in the long distance limit or in the soft limit, this interaction is completely fixed. So that, okay, said that, one may think that this should also rule out massive high-spin particles as well. For example, one may just argue that if I'm performing very high energy experiment, any light high-spin particles will approximately look like massless particles. So these arguments should be applicable there. But of course, that's not true. The reason is there is a discrete difference between massive and massless particles of the same spin. They have different number of degrees of freedom. For example, in 4D, a massless particle has just 2 degrees of freedom, whereas a spin J massive particle has 2 J plus 1 degrees of freedom.
I'm sorry for interrupting, but
yeah.
Still I don't quite understand or follow your argument, because yeah, okay, one massive particle in the high energy limit is not a single massless, but still it's a number of massless particles, just in accordance with this counting. So what is your argument?
I'm saying that like, they are not. So basically that will tell me that how many massless degrees of freedom you can have at high energies, but it will not exactly tell you the number of what the spins are, things like that. So I'll actually give you a more robust argument for massive particles anyway. So this is the goal of this talk is basically to actually just goal of this talk is just to show you that there are similar bounds for massive high-spin particles as well, as long as they are somewhat elementary.
Okay.
So in general, massive high-spin particles are not ruled out, but that does not mean that there are no constraints on massive high-spin particles from general principles. All the constraints, they come from the fact that there is a conflict between massive high-spin particles and causality. There are a couple of examples available already in the literature. So for example, in this paper by Kamanho, Edelstein, Malasena, and Zaveda from 2014, they showed that if you have a tree-level scattering amplitude with higher spin exchanges, you must exchange an infinite tower of higher spin particles with unbounded spin, otherwise it will violate causality. In the second paper, Karen Hoyt, Komargorsky, Sever, and Zaviadov, they showed that that's not sufficient. If you then want to have a consistent S matrix, then because of this infinite tower of exchange of higher spin particles, the amplitude in the high energy limit has a unique asymptotic behavior. And also with my collaborators, I actually showed that any finite number of massive high spin particles that are elementary or approximately elementary, they're ruled out. And I'll actually explain all these results in more detail. Okay, now one may ask, why should anybody care about massive high spin particles? Or why do I care about massive high spin particles? First of all, we don't see any massive high spin particle in nature which look even approximately elementary. So there might be a very good reason behind it. Said differently, let's say there is some experiment tomorrow that detects a massive high spin particle which looks almost elementary. So what can I conclude from that observation? This seems to be an interesting question to me, but there is one more reason why high spin particles can be of interest, because they are related to a much bigger question that is of interest to many high energy theorists. So can we access some part of quantum gravity or some aspects of quantum gravity directly from QFT? This is definitely a difficult question. For example, one can ask, is it possible to derive stringy amplitudes directly from QFT consistency conditions? Actually, these higher spin particles, they provide a bridge that connects QFT with quantum gravity. And you can actually derive some stringy amplitudes directly from QFT consistency condition with the help of high spin particles. And that's basically what I'm going to explain today. More precisely, I will argue that theories of stable or metastable high spin particles can be coupled to gravity while preserving causality only when the gravity sector has many of the properties of fundamental strings. So my first goal will be to define precisely what I mean by theories of stable or metastable high spin particles, by causality and stringy gravity. And my second goal would be to actually argue that this statement is a true statement. And at the end, if I have time, I'll discuss large N QCD, because in large N QCD, you have blue balls and mesons of unbounded spins, which behave almost like elementary particles. So we might be able to say something about that as well from this statement. Okay, let me begin by defining by what I mean by theories of metastable high spin particles. So I have a QFT, and lambda QFT here is a cutoff scale in the in QFT, but I'm not assuming there is a cutoff scale. It can be a UV complete theory, but in that case, lambda QFT can be infinitely large. And there are many particles in the theory which I denote by this symbol GJ. There can be particles with spin less than 2, but there are definitely particles with spin greater than 2 as well in the theory. So first of all, by a theory of metastable high spin particles, I mean that below the cutoff scale lambda QFT, these GJ particles, they represent all degrees of freedom of the theory below the cutoff scale lambda QFT. And these particles, they are metastable. By that I mean that all the couplings, all the effective low energy couplings are small. So for example, this 3-point interaction of 3 GJ particles, it's suppressed by some small parameter lambda. And obviously, I'll also assume that this QFT has a consistent S matrix. By that I mean just the standard. The S matrix has standard properties such as it agrees with unitarity, crossing symmetry, causality, things like that. Then eventually I'll couple this QFT to gravity. So the gravity sector obviously has a spin 2 massless particle, which is the graviton. But I'm also allowing the possibility that there can be other particle in the gravity sector. Of course, I'm not forcing that there has to be a high spin particle, other high spin particles in the gravity sector. I'm just allowing the possibility that they can be there. And lambda GR, it represents the mass, it is the mass of the lightest higher spin particle in the gravity sector. And I also assume that even when I couple this higher spin QFT to gravity, these GJ particles, they remain metastable. So by that, I mean like couplings like a GJ particle decaying into 2 graviton. Obviously, it's already suppressed by 1 over m Planck square just from m Planck counting. But the coefficients such as lambda g, they are not too large. They can be order 1 or something like that, but they are not so large that they break down the perturbation theory. Okay. There is so since I'm talking about 2 different sectors. There is a QFT sector and there is a gravity sector. Let me make it more precise. So if I take any GJ particle in the theory and consider a 2-to-2 scattering of that GJ particle, and if I make M Planck to be infinitely large to begin with, since these particles are, since the theory is weakly coupled, at the leading order, I only have tree-level scattering amplitude, and the tree-level scattering amplitude is a monomorphic function with simple poles, which are located at the position of GJ particles. So what I mean is the following. So if each pole in the scattering amplitude, they represent the exchange of a particular GJ particle, which can be the same GJ particle or which can be a different GJ particle. So that's all you. These are all the poles that you have in the scattering amplitude. Now let me make M Planck to be finite. The scattering amplitude now must develop new poles. It must develop at least one new pole which corresponds to a graviton exchange, because all particles must interact with graviton in the same way. But the amplitude may develop other new poles, other new T-channel poles. So these other new T-channel poles, they will disappear when you take the limit M Planck to infinity. But when M Planck is finite, these other new T-channel poles can be there, and they should be thought of as new particle. They should be thought of as particles in the gravity sector, which are different from the graviton. My first goal would be to argue that these additional gravitational poles are essential to the preservation of causality when we couple a theory of metastable high-spin particles to gravity. So this is the outline of the rest of the talk. Let me leave it here for a few seconds, and let me pause for questions in case you have any questions.
Sorry, can you say it again, like based like on which criterion do you separate particles in 2 sectors? By their strengths of interaction in M Planck, or what?
It's basically like, as I said, like just by looking at the 2-to-2 scattering amplitude. So when you make M Planck to be infinitely large, or basically then you have certain set of poles in the scattering amplitudes, simple poles in the scattering amplitude. So when you make M Planck to be finite, so there can be other poles in the scattering amplitudes. These are basically the particles in the gravity sector.
So they disappear for M Planck. So they disappear in one region because their couplings vanish, or what?
Yeah, so something like that. Yes, exactly.
And here, GJ, is it from gravitational or from QFT sector?
GJ is always from the QFT sector.
Okay. And concerning stability, you formulated it in terms of couplings. But normally,
can you say that again?
Like the condition for stability, you formulate it in terms of 3-point couplings, I guess. Yeah. But I would say that normally you formulate in terms of like whether mass has imaginary component or not.
Yes, you can do either. Like it's not like I phrase that it in terms of couplings just because like it will be easier for me to utilize later.
Okay, thank you.
It's technically more easier for me to actually implement.
Thank you.
I have a question.
Yes.
There are many stable With high spins.
Yes.
What's wrong with them?
Oh, okay. So that's, let me go back to, okay. So basically, the cutoff scale, if you write down a theory of this high spin composites, the cutoff scale will be comparable to their masses. So since, as you can see from this slide, that the theory that I'm discussing, they are basically, the cutoff scale is much higher compared to the masses of these GJ particles. So
they
that's
exist in QCD. Sorry, they exist in QCD, and you don't have any cutoff scale in QCD. QCD is a perfect theory.
Yes, but like you get higher spin particles only. Let's say in the large N limit, you get higher spin particles when you have composites.
No, I have nuclei, n equals 3.
Yeah, but even there, like when you write down an effective theory for this nuclei, that theory has a cutoff scale.
Theory, I write QCD. I'm sorry, I write QCD, and in QCD I have no cutoff and a lot of massive high spin nuclear particles.
Yes. So when I define this theory this particular way, yeah, you can talk about QCD. In that case, obviously there will be composites, but since by definition I'm saying that these GJs are all the degrees of freedom in the theory. So basically, in some sense, the theory I'm talking about here, below the lambda QFT scale, you will not be able to tell if these GJ particles, they are composite or elementary. So they are basically, in another way of saying it, that these GJ particles, they are effectively elementary. They are basically, you will not be able to perform any experiment below lambda QFT to actually say if they are elementary or not.
What does it mean in formulas?
In formulas, it's basically when you write down an amplitude like this. So below the lambda, the cutoff scale, you'll only see basically poles at the location of these other GJ particles. You'll not see like poles which are because of the things that GJ particles are made of. And yeah, so there is another way of saying it.
What do I mean by made of? I mean, there are nucleons,
yes,
protons and neutrons, and they are the same in the same class, right?
No, because like when you let's say if you consider the scattering of these nucleons, and as you increase energy, you'll actually be able to tell that this nucleon, they are not elementary, they are composites.
So what does it mean? This mean in formulas?
Basically, let's say when you consider a scattering amplitude like a nucleon going to a nucleon, and it something like this. So GJ H mu nu. If you consider some interaction like this, and so this basically is completely fixed by symmetry, but there are coefficients. So the fact that these GJ, they are effectively elementary or not, they comes from the fact that what are the form factors for this amplitude. So as you increase the energy, so you can actually just from the form factor, you'll be able to tell that if these GJ particles, they are effectively elementary at the energy scale of m, where m is the mass of this GJ particle, or not.
Right, but you didn't try this as an assumption or anything like that, right? You didn't consider scattering at energies comparable to to masses of these particles. Something like
that. So basically, I'll study scattering amplitudes where basically at the energy scale which is larger than the mass of the external particles. So basically, that's how I'll be able to tell that if they are effectively elementary or not. So this is the setup I'm working with. So this will not cover things like nucleons, for example, but it's basically, it will cover anything which looks elementary at low energies, or at energies comparable to their masses. So the entire setup is designed for that.
Oh, yeah, okay.
Okay, let me move on. Okay. Now let me explain what I mean by causality. In classical physics or even in quantum mechanics, causality is somewhat of a trivial statement because generally we impose causality by hand. But in QFT, causality is a non-trivial statement because in QFT, causality basically requires that commutators of local operators in Minkowski space, they must vanish if the operators are space-like separated. And this is a non-trivial statement, especially because this is an operator statement. So I can just take this operator or this commutator, and I can just plug it inside any correlator I like. That correlator must also vanish. So that gives us an infinite set of consistency conditions that any Lorentzian correlator must satisfy. Because of that, causality is a non-trivial statement in QFT. There are two main facts that I want to emphasize throughout the talk. The first statement is there are QFTs that appear to be causal in the vacuum state, but they can violate causality in non-trivial excited states. And since causality is an operator statement in QFT, so a system must be causal in every state of the theory. And the second statement that I want to emphasize is the following. QFTs that appear to be causal in flat space-time can violate causality when coupled to gravity. Okay. Then I actually want to emphasize that it's not just a conceptually important principle. Causality can actually be utilized to derive really non-trivial constraints about various kind of QFTs. For example, in conformal field theory, you can derive general bounds starting from causality or requiring causality.
Excuse me.
Yes.
Can I ask a question?
Yeah.
At this point. Well, so you define causality with respect to just normal Minkowski cone and Minkowski space.
Yes.
And probably you do something the same in the gravitational field. So you have your metric tensor that defines the causal propagation, isn't it? Is that the point?
When I say that I'll couple QFT to gravity, I mean that it's basically a flat space theory with a graviton. So it's basically the light cones, they are basically still the flat space light cone.
Yeah, what I mean actually in different language, this may work, may not work, because if you introduce higher spins, the string theory, for instance, then interactions may contain higher derivatives. Yeah, and actually propagation may not follow the standard low energy prescription we are used to. So the issue of causality may be very different from that. So so there is always an issue like that when higher spins are around.
So you mean by so basically you are saying that it can generate higher spin things like R square, things like that. I guess that's what you're.
This is a very, very minimal way that can thing that can happen. That it may be much worse.
Okay, go ahead. So basically, I would say that since you are still expanding around flat space,
yeah,
it still must respect the flat space light cones basically. So now, if you go beyond, if you expand around any other background, even like a small deviation from flat space, then I completely agree. It's more complicated than that. But when you expand around the flat space background, it's basically you still be able to treat that as a theory, as a theory of like spin to massless particle in a flat space time.
Yeah, I agree. Okay, thank you.
So the main reason for showing you this slide, I'm not going to explain any of them. The main reason I'm showing you this slide is basically just to emphasize that you can derive really non-trivial statements just by imposing causality, just by imposing the statement of causality in position space correlators in Lorentzian signature. This is by no means a complete list, but you get the idea. But there is obviously a technical problem. Generally, in QFT, we don't actually compute position space correlators. In CFT, we can. So because of that, you can actually utilize the causality in CFT in various different ways. But in general, we don't compute position space correlators. We compute scattering amplitudes. And there is a similar but not exactly equivalent statement of causality for scattering amplitudes. Let me explain that. You can just take any 2-to-2 scattering, as shown here. S, T, U, they are the standard Mandelstam variables. And we are in the limit where S is much, much larger than T and all m square of all external particles. Then we can just go to the impact parameter space by integrating over the transverse momenta, and we get a function of S and impact parameter B. So this is often known as the phase shift. The phase shift actually has some really nice properties. For example, in the tree limit or tree level, where you only have tree level amplitudes, you can actually show it very easily that phase shift only gets contribution from T-channel poles. So the contact diagrams or S or U or other poles will not actually contribute to the phase shift. Only T-channel poles contribute to the phase shift at the tree level. And another nice property of the phase shift is that physically it's related to the Shapiro time delay. So generally it's expected that this quantity has to be positive for a theory to be causal. Actually, this can be made more precise. This can be made precise just by mapping an Eikonal scattering to a signal transmission problem. So you have some incoming state or incoming signal, some scattering goes on in between, and you have some outgoing signal. So the incoming signal, we designed it such a way that it does not have any support for V less than 0. For U and V, they are the standard light cone coordinate. So in this context, causality is basically just will tell you that the out signal must not have any support for negative V as well. Again, we are in flat space. So from this requirement, you can derive some analyticity condition for the phase shift and also some positivity condition. Is basically you can show that the phase shift is bounded in certain regime of the parameter space or certain regime in the complex S-plane. From there, you can actually derive two conditions on this phase shift. When S is much, much larger than 1 over B square, where B is the impact parameter, or M square, where M square of all external particles, the phase shift must not grow faster than S. And the second condition is when the phase shift grows linearly in S, it must be positive. Actually, in ADS, let me make one more comment. These two conditions, I don't know of a way to derive them directly from the commutator condition of causality. Probably it can be done, but I haven't seen anybody shown it explicitly. But there is something nice goes on when we go to ADS. What you can show in ADS is that in ADS, you get these two same condition in the bulk, where you can actually relate these causality conditions to the causality condition on the dual CFT. So you can actually show that if you violate any of these two conditions in the ADS bulk, it basically in the dual CFT, you can show that there are some commutators of space-like separator operators that becomes non-zero. So in ADS, actually, you can actually map these two conditions of causality to one onto the other one. Let me now use these conditions to actually impose constraint on theories of metastable high-spin particles coupled to gravity in 4D. I'll basically perform 3 thought experiments. First, it's a thought experiment where the incoming particle is a GJ particle and an H, and the outgoing state is basically again a GJ particle and the graviton, where the incoming and outgoing polarizations are the same. So we begin by computing the phase shift. And as I said before, since only the T-channel poles contribute to the phase shift, basically in the leading order, this phase shift is given by this 3-point vertex and this 3-point vertex on shell. And that makes it really easy to compute. The reason is on-shell 3-point amplitudes are completely fixed by Lorentz invariance. So when this is, for example, when this is GJ, and this is H, this 3-point on-shell 3-point amplitude is given by a linear combination of this 2J plus 1 structures which are completely fixed. So in general, what you can write down is basically this expression where this 3-point amplitude is a linear combination of this 2J plus 1 structures with some coefficients AI. For these AIs are in general, they are arbitrary. That's actually not completely true. For example, you still have to satisfy soft theorems. So the leading order soft theorem will tell you that A1 has to be 1. Similarly, subleading soft theorem will tell you that AJ plus 2 has to be J, things like that. But all the other coefficients, they are completely arbitrary so far. Now I can just use this 3-point amplitudes. I can just compute the phase shift. I can, first of all, you can easily show that this grows linearly in S. So you can use the positivity condition. What it will lead to is the following. It will actually dictate that all these small a coefficients, they are completely fixed by causality. If you impose causality for all possible external polarization, they'll fix these a coefficients completely. So that means basically this 3-point amplitude, it's completely fixed, up to some corrections that I'm going to talk about next. Since this is kind of an important result for this talk, let me make some comment about the correction term. So you can also show that only corrections that you can get for these results, they are suppressed by lambda gr. If you remember, lambda gr is basically the mass of the lightest particle in the gravity sector. it's the lightest higher spin particle in the gravity sector. So other than this correction terms, the amplitude is completely fixed. Actually, there is something really interesting going on, which I don't have an explanation for. So this fixed structure here, this is there is another unique structure people can define. So recently, Arkani, Ahmed, Huang, and Eikonal showed that there is, when you study gravitational interaction of Kerr black holes in the classical limit, in the long distance, in the large distance limit, this interaction is also completely fixed, and there is an unique structure there as well. So somehow this fixed structure that we find, they match with that structure that Arkani, Ahmed et al. Found in their paper. And there is no good explanation why these two structures match, because I can do the following exercise. I can replace these GJ particles by some classical Kerr black hole, and I can run the same argument. It's actually not very difficult to show that all the corrections terms that you get for Kerr black holes, they are comparable to this fixed structure. So that means basically there is no reason why you can trust our argument for external Kerr black holes, but somehow our unique structure matches with their unique structure. And I'm sure there is a good reason why these two structures match, but I have no idea why why they match.
Hello, I have a question.
Yeah.
Like for Kerr black hole case, like there can be some structure of the black hole which also can give some tidal effects, and
yes,
it can couple to H mu in different ways. So how you can tell that it's completely fixed, this 3-point function?
It's not okay. So that's not yeah. So probably I should have been more careful. So what they showed is basically for Kerr black holes interaction. So there is a part which is completely universal, and there is a part, as you said, which is kind of theory dependent in that sense. So the part which is completely universal, that matches with this structure I'm talking about.
Okay. Okay, thank you.
Let me perform my second thought experiment. It's exactly the same as the first one. All I do is basically replace the incoming GJ particle by a coherent state which is created by a superposition of two different GJ particles. I can again run the same thought experiment. I can again impose the same positivity condition. And I get a bound on this scattering amplitude. There is another way you can think about this bound. Positivity of the phase shift, it allows you to define a positive inner product, which comes with a Cauchy-Schwarz inequality. This is basically the Cauchy-Schwarz inequality. And if, so this Cauchy-Schwarz inequality, when I try to make this consistent with Graviton's soft theorem, it tells me the following thing. So it tells me that this 3-point amplitude, this on-shell 3-point amplitude, which is basically, you can think of as if it's a graviton induced mixing between two different GJs. It's suppressed by positive powers of 1/λ GR. So it was actually very surprising to me. Somehow, the graviton induced mixing between two GJ particles, they are suppressed by higher spin states in the gravity sector. Of course, I should definitely mention that this argument so far, it does not require higher spin states in the gravity sector. So it's completely consistent so far to actually make λ/gr infinitely large and tune all this graviton induced mixing to be exactly 0. So that's completely consistent so far. But next, let me perform the third thought experiment where I actually impose a bound on this lambda gr. The third thought experiment is basically exactly the same as the first two. It's just basically a more complicated version of the previous two thought experiments. In this case, all the external states, they are coherent states created by superposition of higher spin particles plus gravitons. And again, I'll perform same kind of argument. And this time it gives me a bound on this scattering amplitude. So basically it gives me a bound on this scattering amplitude for two GJ particles. The incoming state is two same GJ particles and the outgoing state is two gravitons. And the bound is, and this amplitude is bounded by 4 GJ scattering amplitude times 4 graviton scattering amplitude, up to some order 1 coefficients, which I'm ignoring for just for sake of cleanliness. Now, this is not clear to everyone at this point, but this is actually a really difficult inequality to satisfy for the following reason. You can actually show that so whenever I'm writing down this inequalities, I always mean I'm computing the phase shift related to this particular Feynman diagram. So the reason this is actually kind of difficult to satisfy is the following. You can actually show really easily the phase shift for the right hand side diagrams. Both of them grow as linearly in S, because the KFT sector and the gravity sector, they are consistent with causality independently. But you can actually, it's really easy to show that the phase shift for this amplitude, it grows as s to the power j minus 1. So that means for j greater than 2, it looks like it's kind of impossible to satisfy this inequality. Actually, this can be made more precise. The only technical problem is so far everything is theory independent. So I actually don't know anything about this 4-point processes. But I can still make some progress just by parameterizing this particular 4-point scattering amplitude. Obviously, this 4-point amplitude has two parts. There is a graviton exchange, and there is this exchange of other GJ particles. The graviton exchange is completely fixed from the first two thought experiments. So that's the gravitational part of the amplitude. But the non-gravitational part of the amplitude that comes from these GJs, that we don't know anything about that, but we can parameterize it. So in this specific regime, we can always parameterize this amplitude as this s over mj square, where mj is mass of the external GJ particles, some coefficients small gj square, and some power aj. So this small gj square and aj, they are theory dependent. So we don't know anything about them to begin with, but we still know that aj has to be less than equals to 1, but that's it. We don't know anything more about these two coefficients. They are theory dependent. But as I said, we can always parameterize this non-gravitational part of the amplitude this way. The reason this is important is the following. So the relative strength between this gravitational and non-gravitational part of the amplitude will play an important role in the bound that I'll discuss next. So now first consider the case where the gravitational part of the amplitude is larger than the non-gravitational part of the amplitude. Then if you try to satisfy the bound that I derived, for j greater than equals to 3, you can show very easily the only way you can satisfy this bound if lambda gr is on or below mass of this gj particle. So that's the only way this can be satisfied for all these gj particles with spin greater than 2. Now let me look at the other limit. So okay, so this obviously has the implication that there is no QFT description where you can actually integrate out all these high spin states in the gravity sector and get a theory of this gj particle coupled to graviton. So that description does not exist in this case. Now let me look at the other limit where.
Sorry, could you please explain like the previous slide to this one? So how do you, like the previous one, non-gravitational part? Yeah, how do you fix the form? So where this comes from, like s over mj squared to power aj?
So okay, since like I'm fixing probably like this is, I should have mentioned this, like I fix the impact parameter to be exactly 1 over mass. So we don't have, basically the only scale that you have is basically s and the mass of the external particles. That's it. So everything else you can just keep inside this gj or this a. There is only one subtlety which I skipped just to make this simpler. It's basically, obviously, since this is an amplitude of high spin particles, there should be polarization tensors everywhere. So I'm ignoring this polarization tensor in the following way. So I'm not writing down the most general amplitude you can write down for any polarization tensor. It's basically I'm fixing the external polarization to be something, and for that particular external polarization, you can always write the amplitude in this form, because just from whatever the variables you have in your hand.
But is it in some limit, like, because you draw an exchange here, it's supposed to have a pole, for example, right? So this is because square root of s is much larger.
Okay. Oh yeah. So there is one more step. So there are poles, but since we are in the impact parameter space, it's basically now it's only a function of impact parameter b and s. That's it. So all the poles that you have for exchanges, they basically gives you a specific behavior for the in terms of impact parameter. So in the impact parameter space, you don't see any poles. So for example, even you can just look at the gravitational part of the amplitude. Even there, you don't see any poles, because the poles, whenever you have a pole, that contributes to the phase shift, but the phase shift that you get, that does not have that pole. It basically gives you some specific functional form.
Okay, thank you.
Yep. Okay, now let me look at the other limit where gravitational part of the amplitude is smaller than the non-gravitational part of the amplitude. And in that case, even for j greater than 3 or j greater than 2, you can show that now lambda gr can be parametrically larger than mass of the external particles, but still it's much below the Planck scale. So basically now you have a precise bound. Even in this case, you have a precise bound, but that bound says that it has to be much below the Planck scale. To show it graphically, it gives you something like this. So when lambda gr is greater than lambda or when the gravitational part of the amplitude is greater than the non-gravitational part of the amplitude, there cannot be any parametric separation between lambda gr and mj. So only things in the shaded region they are allowed. Everything else they are ruled out. The only way there can be a parametric separation between lambda gr and mass of the external particle if the gravitational part of the amplitude is smaller than the non-gravitational part of the amplitude. And this plot is specifically for j equals to 3. Now, if you increase spin, it actually gets flatter. So it becomes more and more constraining. Actually, I'm running out of time, so let me summarize whatever I said so far. Higher spin metastable particles cannot couple to gravity while preserving causality unless there exist higher spin states in the gravity sector much below the Planck scale. Actually, I had planned to show something else as well, which probably I'll not have time to talk about. So let me just briefly mention what more you can say. Since now you know for sure, when you couple metastable higher spin particles to gravity, there has to be higher spin states in the gravity sector much below the Planck scale. From there, actually, you can say a lot about the underlying UV complete theory, just from S-matrix consistency conditions. That you can do that because there is a really nice uniqueness theorem by Kernhout, Komargovsky, Sever, and Zaviedov, which basically says that in the weakly coupled regime, if you exchange any higher spin particle in a scattering amplitude, the amplitude is completely fixed for large T and large S. Not just that, that fixed amplitude coincides with tree-level string theory. So we can just use that theorem, and that theorem can only be used if we assume the following properties of the gravity sector of the full theory. So we assume that the UV completion is weakly coupled, it's unitary, it's Cosin symmetric, it has the standard Regge asymptotics, and there is no accumulation point in the spectrum such that there is a standard or well-behaved thermodynamic limit. If you just assume that and invoke the CKSZ uniqueness theorem, you can actually show that the gravitational part of the amplitude must have the following properties. The leading Regge trajectory for large T, it's asymptotically linear. It has to be asymptotically linear. The second thing you can show that the gravitational part, so basically you can show that there is an imaginary part in the gravitational amplitude even when impact parameter is large. So that basically tells us that there has to be extended objects in the theory since the imaginary part of the gravitational amplitude is non-zero. Moreover, the most importantly, you can actually, as I said earlier, so you can completely fix the amplitude for large S and large T. It must have this particular form. And this is nothing but the tree-level Grossman amplitude. So this is basically the large T, large S limit of a closed 4-point scattering amplitude. So you can say all this about the gravity sector of the theory when we couple metastable high spin particles to gravity. Not just that, obviously, there has to be an infinite tower of asymptotically linear, parallel, and equispaced Regge trajectories, which agrees with tree-level closed-string theory. So since I don't have time, let me just go to the conclusion. Okay, so the first thing that I want to emphasize at the end, it's basically the statement that I made in the beginning. QFTs that appear to be causal in flat spacetime can violate causality when coupled to gravity. And philosophically, the thing that I find most interesting is the following. It appears that QFT consistency conditions know a lot about quantum gravity. And this is really surprising to me. Probably this should not be surprising since like we all know about ADS safety correspondence, but still the fact that some aspects of quantum gravity emerges from QFT when we have just introduced high spin particles, this still is kind of surprising to me. More precisely, I argued that theories of metastable high-spin particles can be coupled to gravity while preserving causality only when the gravity sector has many of the properties of closed strings. This part I actually did not have time to actually show you, but probably you can guess where this statement comes from. It's basically metastable high-spin particles in 4D with masses below the string scale must satisfy with gravity conditions, because as I said before, the gravitational part of the amplitude and the non-gravitational part of the amplitude, their relative strength actually tells you what the string scale is compared to the mass of the particles. Also, I didn't have time to actually explain, but these bounds also have surprising implications for large NQCD coupled to gravity. We wrote a paper, I think last month. If you're interested, you can check that paper out. And let me finish here. Thank you.
Thank you. Are there any questions?
I have a question concerning the last point. Indeed, in QCD at large n, there are lots of resonances with high spins.
Mm-hmm.
And the scale of QCD is much below the Planck scale, right?
Yes.
So how does your do your previous results match to this simple property of large n QCD?
So if in the real world QCD, obviously our bound does not apply to real world QCD at all. Just because like where where the cutoff scales are, where the resonances are, things like that. But for in the large n limit, we can actually say something more. Actually, since you asked this question, let me go back. So what you can, so in the large n limit, basically in the low energy, what you have is basically metastable glue balls and mesons of arbitrary large span. So we can actually apply our argument to these glue balls and mesons. So our argument applies there. So if you do that, you can do that just by replacing these external GJ particles by, let's say, a glue ball of spin greater than 2. And I can actually run the same argument as I discussed through the talk. It will say the following thing. It will tell me that when I couple large n QCD to gravity, and this is the scattering amplitude that you'll get at the leading order. I'm ignoring the contact diagram just because it will not affect the argument at all. So our argument will actually show that will show that this scattering amplitude by itself is inconsistent with causality. So basically, our argument will then tell you that there has to be additional T-channel poles that are there, which makes this amplitude consistent with causality. You can actually do that two different ways. So for large n QCD, actually, we cannot say which of these two scenarios is the right one, but we can actually say that these are the two scenarios that can make this diagram consistent with causality. First scenario is basically when GJ is a glue ball. So basically, just from the consistency condition, you can show that there are kinetic mixing, something like this. And also you can show that a decay of a glue ball to 2 graviton, it actually is enhanced by n in the large n limit. So these two effects can, in principle, actually make the previous diagram consistent with causality. But it's not possible to actually check if they actually do restore causality. there is another process which actually can make the previous diagram consistent with causality. It's basically, since one might argue that since the problem comes from the gravity sector, but just from the exchange of a graviton, probably it's more reasonable to actually solve this problem by adding new states in the gravity sector. And actually, you can show, just as I argued toward the top, just adding high spin states in the gravity sector can actually make everything consistent with causality. In that case, you get a bound on the string scale. It's basically bounded by this expression in the large L limit. But again, I have to stress that just from our argument, it is not possible to say which of these two scenarios is responsible for making the thing consistent with causality. Or finally, I can just say that like these two scenarios has something in common. So if n is larger than m Planck over lambda QCD, actually you can show that both scenarios implies the theory has a stringy description if gravity is weakly coupled. So this is all you can say about large N QCD. Any other question?
Well, the first option should be possible to check, right? Last option. I mean, once you know QCD and
yes, in principle, yes.
Coupling of energy momentum tensor to H mu nu, then you probably can figure out what are these.
Actually, from there, you get some kind of a sum rule. So you get like sum over all spin to glue balls, things like that, like some such like such as that equals to something. It does not actually tell you individual mixings. So for individual mixings, actually you have to do a more rigorous computation that I'm not aware of how easy it is to do. But in principle, it's actually like this can be checked.
And the left sounds pretty weird because you know, the string scale is a string scale, QCD scale is a QCD scale, and they need not be related to each other, right?
Yeah, that's right. So even if like, okay, so there might be two different ways of thinking about it. Just from the low energy perspective, it looks completely bizarre to me that like how QCD interactions can actually restore causality with violation, which comes from like gravity exchanges, which has like different scale and different dynamics. But one can also argue just from looking from the UV perspective, like you have large N QCD to begin with, which is UV complete, which does not have any problem. So when you couple it to gravity, probably like you get this magical cancellation anyway. So I don't know which is the right way of thinking about this, but like probably you can argue both ways.
So you discussed high spins, but could you comment on causality constraints for low spins? For example, if you have a scalar field theory or vector, if you look at high point amplitudes, it's known that you can constrain certain terms in effective action.
Yes.
Using causality. So what about high point amplitudes here as well?
By higher point, you mean like something like 4 scalar scattering amplitude, things like that?
Yeah,
or like...
yes. So the kind of non-minimal terms which you can have in effective Lagrangian, which may break causality. Yeah. So they should be visible from high point amplitudes, probably.
Yes. So unfortunately, for scalars, you cannot say anything from causality. So for example, even if you try to derive the standard bound on del phi to the power 4th, which comes from unitarity, if you try to apply this argument to that, it does. You will not be able to see that violation. So
what about vectors? For vectors?
Yes. So for vectors, or even for let's say massive spin 2, you can actually run this argument. And what it will do is the following. Let me see. Okay. So what it will do is the following. It will basically constrain any 3-point amplitude like this. Even when X is a spin 1 massive or spin 1, or even when it's like massive spin 2, you can actually constrain this particular 3-point amplitude. And actually what you get is basically the statement that all the higher derivative interactions that you can write down in your effective field theory, they must be suppressed by something like a string scale. So just from these interactions, that's what you get out of causality.
Does this mean that you forbid form factors?
For which example? So let's say for a scattering amplitude like x going to h, you mean like what can I say about the form factors?
Yes.
Okay, so that's where the statement about elementariness comes in. So all the statements from causality, even for spin 1 or spin 2 or higher spin, it's basically it basically applies only when these form factors that they are not there for energy comparable to the mass. So basically, when you look at the scattering amplitudes at energy scale comparable to the mass of the external particles, they must look elementary for this argument to work. So there can be form factors which can lead to additional poles. So they will then contribute to the phase shift. Then this argument does not work.
Yeah, but there are form factors, right? Due to loop contributions to the vertex, right? So
yes, so
they are suppressed in the weakly coupled theory, but they are there. They are there.
Yeah, so there has to be some kind of suppression that has to be there. So that's why like they cannot be composites. They'll should look like effectively elementary in the energy scale of their mass, basically. So whatever loop effects there can be at high energies, they have to be suppressed by some coupling constant or something like that.
Any other questions? Okay, if no questions, then let's thank the speaker. Yeah, thank you. You can clap any way you can. Yeah, and thank you everyone for coming, and see you next time.
Thank you for the invitation.